So now that last talk by Nicholas Andruskiewicz, he will talk about the pointed Hopf algebras of odd dimension and Nichols algebras over solvable groups.
Thank you. And thank you for the introduction, and thank you the organizers for the invitation to Beijing and to the meeting. I will start by the main result. Let me first say that the Hopf algebra is pointed if every simple comodule is one-dimensional. This seems to be a very restrictive condition, but in fact, it covers very important examples of Hopf algebras. For instance, group algebras are pointed, enveloping algebras, quantized enveloping algebras, of Lie algebras or of Lie superalgebras, and the finite dimensional versions of these quantized enveloping algebras are all of them are pointed. So the problem that we are working after many years is the classification of the pointed Hopf algebras under the assumption that they are finite dimensional. For that, we start by observing that there are three very basic invariants of a pointed Hopf algebras. The first basic invariant is the group of group-like elements, which is the x in H, which are non-zero and satisfy this condition. This is a classical invariant of any Hopf algebra, pointed or not. The second one is the infinitesimal braiding, which I will not define. And this is a Yetter-Drinfeld module over the group algebra of G of H. Yetter-Drinfeld module means the module over the double, over the Drinfeld double. I will explain this later. And the third invariant is constructed starting from the second one. It's called the Nichols algebra of the infinitesimal braiding. So the Nichols algebra is a graded algebra which is connected in the sense that in degree 0 you have only the field, and it has a structure of Hopf algebra in the category of Yetter-Drinfeld modules over the group algebra of G of H. As a matter of fact, if you take the Nichols algebra, you perform an operation which is called the bosonization, which means that you take the tensor product of these two objects and provide this with some specific algebra and coalgebra structures, then this is a Hopf algebra which is contained in the graded algebra G of H, which is associated to the coradical filtration of H. So without remembering all details, we have these three invariants. Okay. These invariants constitute the core of the approach to the classification of pointed Hopf algebras that we proposed in 1998 and 2000 in two papers. And one of the results, I will assume from now on that the field is algebraically closed and of characteristic 0. And one result in this, under this assumption that we obtained is the classification of the finite-dimensional pointed Hopf algebras such that G of H is abelian, and the order of the abelian group G of H is coprime to 210. So 210 is, of course, 2 times 3 times 5 times 7. Now, this result, recently we are able to extend it to the following theorem. First, suppose that you have a pointed Hopf algebra which is finite dimensional, and assume that the dimension is odd. Then, first, the infinitesimal braiding B of H is a braided vector space of diagonal type. I will explain what this means later. Second, the Hopf algebra H as an algebra is generated by the group-like elements, the elements of G of H, and skew primitive elements. This is equivalent to say that this bosonization, which I told you before, equals, in general is a subalgebra of group of H, it is really equal. Now, there is the way to go from group of H to H is called the lifting, and the third point is that this lifting is always a cocycle deformation. And the final point is that if the greatest common divisor of D and 105 is 1, so D is not divisible by 3, 5, and 7, or then the defining relations of H are explicit. And they are either quantum set relations, linking relations, which I will not explain, and powers of the root vectors, which I will also not explain. So this is, in some sense, our main result. What does it say? It says that, I will explain in the next slide what it says. I want to give an example of how is this situation. Suppose that you have a primitive n root of unity where n is, for simplicity, is odd, and take H the UQ of SL2. Then group of H is B of V smash the group algebra KCN, so Cn is the cyclic group of order n, and V is a braided vector space of diagonal type with this braiding matrix, so that B of V is generated by X and Y with these three relations: X to the n, Y to the n, Xi minus P minus 1 Yx. And group of H is K of X, Y, G with these relations, and this is the action of G. However, this is not the same as UQ of SL2 because there is one relation that was deformed. So this is deformed to this relation. And we can also deform the powers depending on the group. For instance, if you instead taking the bosonization with the cyclic group Cn, you take the bosonization with Cn square, then you can deform this also. Okay. So suppose that the I skipped this one. So this theorem 1 that I told you before says that if you have a pointed Hopf algebra of odd dimension, then you can reduce the description of the Hopf algebra to group theoretical information. Now, how do we prove this? Suppose that you have proved 1, the item 1, which says that infinitesimal braiding is a braided vector space of diagonal type. If this is proved, then it follows from results of Anchiono, or in a particular case by Schneider and myself, that H is generated by group-like and skew primitive elements. So the number 2 follows from 1 and previous results. Similarly, 3 follows from previous result by Masuoka and Anchiono and Garcia Iglesias, and 4 follows the defining relations are skew primitive, cocycle are powers of the ones that I explained before, linking relations, quantum set relations, and powers of the root vectors. Then this is also follows from previous result by Schneider and myself. So essentially what I want to say is that to prove theorem 1, we only have to prove item 1. Now, if the dimension of H is odd, then the group G of H has odd order by the Nichols-Seller theorem, which says that the finite dimensional Hopf algebra H is the dimension is divisible by the dimension of any Hopf subalgebra. Therefore, theorem 1 follows from item I, and item I can be rephrased as follows. If G is a group of odd order and V is a Yetter-Drinfeld module over G, then the Nichols algebra, if the Nichols algebra B of V is finite dimensional, then V is of diagonal type. And conversely, if G is a group of odd order, then any finite dimensional pointed Hopf algebra has odd dimension. This is a consequence of the previous result. Now, if G is a group of odd order, then there is a classical theorem by Veit and Thompson that says that it should be solvable. Therefore, theorem 2 really follows from a more general result, which says the following. Suppose that you have a finite group whose solvable radical contains properly the hypercenter. Take a Yetter-Drinfeld module V over the group algebra of G, such that the support of V is a conjugacy class of the group G, and this conjugacy class generates the group G. Then, if the dimension of the Nichols algebra B of V under all these hypotheses is finite, then necessarily V is isomorphic as a braided vector space to one of the Yetter-Drinfeld modules in the list below. Now I have to explain the list before I will explain some terminology of this theorem. The solvable radical is the largest solvable normal subgroup of G, and the hypercenter is the union, the limit of the upper central series of G. The upper central series of G is a nilpotent subgroup, and G is nilpotent if and only if is equal to the hypercenter. And in conclusion, if you have a solvable non-nilpotent group, it satisfies the hypothesis of theorem 3. And therefore, this implies for such a group, theorem 3 implies theorem 2, and for nilpotent groups, this has to be done differently, in a different way, but it also holds. So now I want to give you the list, the list of all Nichols algebras that are finite dimensional over a group with these conditions. To describe this list, I need to remind some terminology. First of all, what is a RAC? A RAC is a set which is non-empty and is provided with an operation with these two properties. It's self-associative, and the action of a fixed element is a bijection. The main example of a RAC is a conjugacy class of a finite group or of a group G with the conjugation operation. One reduces to RACs because the same RAC could appear as a conjugacy class in many groups, in many finite groups, and then by some economy criterion, it's better to just focus on RACs. To construct a braided vector space, which is a solution of the braid equation, or if you prefer, the quantum Yang-Baxter equation, you need a second ingredient, which is a cocycle. A cocycle on a RAC is a function that satisfies this condition. For instance, in this condition is homogeneous in Q, it's immediate that any constant function is a 2 cocycle. Let me give you a couple of examples of RACs. The first example, or the first class of examples, is the class of affine racks. So what is an affine rack? It's an abelian group provided with an automorphism T such that X acting on Y is defined by Y minus T acting on X and T acting on Y. So this is a rack called affine, and it's isomorphic to a subrack of A times the identity of the semi-direct product A by the cyclic group generated by T. Suppose that T is multiplication by some M in zeta, which is coprimed with the order of A, then I will denote FAM instead of FAT. So now the list. The list has first 5 examples of affine racks, which has of the cyclic group Fp with the T is multiplication by D and P is prime. But not every P and every D, only these ones. FPD will be F32, F52, F53, F73, F75. And for all these 5 affine racks, if you take the cocycle constant equal to -1, then the Nichols algebra is finite dimensional. I will say more about this Nichols algebra later. The next example is somehow similar. Is you take F4 instead of Fp, so this is the Klein group, and multiplication by T, where T is the element of F4, which is neither 0 nor 1. This affine rack is the same as any of the 2 conjugacy classes of 3 cycles in A4. And there are 2 relevant cocycles, which I do not have time to explain exactly what they mean, but they are of this shape. Then the next 2 examples are the conjugacy class of transpositions in S4, and the relevant cocycles are epsilon equal to -1 or K4, which I will explain later what is K4. The Nichols algebra of the Bredel space associated to OK2 and K4 is the Fomin-Kirillov algebra FK4. And the one related to FT32 with constant cocycle -1 is the Fomin-Kirillov algebra FK3. And there is another example, which is instead of taking the transposition in S4, I take the 4 cycles in S4. Again, this gives a finite rack that, with respect to epsilon equal to -1, constant cocycle -1, provides a V whose Nichols algebra V of V has finite dimension. I will tell you later the dimensions of all these elements. And these are all. These are the only examples of Nichols algebras of solvable groups. And beyond solvable groups, we know at the moment only 2 examples. One of them is the Fomin-Kirillov algebra FK5, and the other is a relative of this one. And they have this dimension. And it is open whether there is any other Nichols algebra over a finite group which is finite dimensional. In particular, it's an open question where FK6, which is the Nichols algebra of the transpositions in S6 with the same cocycle Chi6, whether this Nichols algebra is finite dimensional. This is open. It is open also where this Nichols algebra is the Fomin-Kirillov algebra FK6. Okay, now I will give some terminology trying to fill the gaps of what I said before. First of all, let me recall the Yang-Baxter equation, which is well known to all of you. And I will use the terminology that the braided vector space is a pair VC, where V is a vector space and C is an automorphism that satisfies the braid equation. And the braid equation is this one, and it's equivalent to the quantum Baxter equation by the rule R equal to tau C, where tau is the usual transposition. Then R satisfies the quantum Baxter equation if and only if C satisfies the braid equation. Okay, I'm going the opposite way. So they are called braided vector space because given a braided vector space, one looks at the braided group Bn, and Bn acts on V tensor n by this rule. You put the identity in the first n-1 tensors, C, which is the braiding in the n plus n plus 1 tensor, and then the identity. And most of the applications of the quantum Baxter equation arise from this representation. Now, Drinfeld found a method 40 years ago to construct braided vector spaces from any Hopf algebra. This is the so-called Drinfeld double, but for us it's better to use the equivalent language of Yetter-Drinfeld modules. So if you have a Hopf algebra H, a Yetter-Drinfeld module over H is a vector space which has a structure of H module, a structure of H co-module, and these two structures are related by this relation. Delta of H acting on V is H1, V minus 1, S of H3, tensor H2 acting on V0, where I am using here the Schüler notation for this expression. So given a Yetter-Drinfeld module, the result of Drinfeld is that in this language, if you take C of U tensor W, of V tensor W equal to you coact on V, and with the H part acts on W tensor the 0 part, then this is a solution of the braid equation, and V is a braid vector space. Assuming the slightly technical condition that the braided vector space is rigid, the construction of Faddeev-Reshetykhin-Takhtajan gives you a bialgebra such that V arises as a Yetter-Drinfeld. Any braided vector space arises as a Yetter-Drinfeld module over bialgebra, and with some more technical work that was done by Hayashi and Schauenburg, you can also have a Hopf algebra. But the Hopf algebra that realizes a braided vector space as a Yetter-Drinfeld module is not unique, and such data, I will call it a realization. Even more, the category of Yetter-Drinfeld modules is a braided tensor category with the braiding given by the analogous formula that the one I told you in, sorry. Somehow I am doing a mistake. With the, an analog braiding, now W is in W, gives that this is a braided tensor category. And in the braided tensor category, one has Hopf algebras, and the Hopf algebras in the braided tensor category are called braided Hopf algebras. Braided Hopf algebras arise in nature by a construction due to Radford, and that was interpreted in categorical terms by Majid. This says that if you have two Hopf algebras provided with a projection from H to K and injection from K to H, such that pi iota is the identity, then you take R equal to the elements in the big algebra H satisfying this equation, then this R is a Hopf algebra, not a usual Hopf algebra, but it is a Hopf algebra in the category of Yetter-Drinfeld modules over the small algebra K. No? So this is it, and then if you have conversely a Hopf algebra in the category of Yetter-Drinfeld modules over K, then you define R smash K as R tensor K with the semi-direct multiplication and co-multiplication. This is a new Hopf algebra called the bosonization of R by K. This new Hopf algebra has maps pi and iota as before, so pi goes from R tensor smash K to K, and iota goes from K to R smash K. So this is an example of this, and these two settings are the reciprocal of the other. So to understand Hopf algebras by some inductive procedure, we need to understand braided Hopf algebras. This is the message of the construction by Radford and Majid of this bosonization setting. And let me explain now what is a Nichols algebra. Start with the Yetter-Drinfeld module V over H, but this can be done also for any braided Hopf algebra. Then take the tensor algebra, the usual tensor algebra. This, you can show that this is an algebra in this category of Yetter-Drinfeld modules, because this is a braided tensor category, so it is more or less obvious. And the tensor product of T of V with itself will be again an algebra, and actually will be again an algebra in the category of Yetter-Drinfeld modules, where the multiplication is the multiplication mu of T of V tensor mu, but here you switch the second and the third terms of the vector. You need 4 vector spaces, so you need the second and the third vectors by C, not by the usual transposition with the usual co-multiplication of T of V, but by this C. Then by the universal property of T of V, you have a unique algebra map delta from T of V to this new algebra determined by asking the elements of V of the vector space to be primitives. In this way, T of V becomes a Hopf algebra in the category of Yetter-Drinfeld modules over V. And when we started to work on this problem, we found the following definition. If you take V a Yetter-Drinfeld module, then there exists a unique graded Hopf algebra R, which is connected, meaning that in degree 0 you only have the field. In R1 you have your initial V. R1 coincides with the primitive elements, and R is generated by R1. So at the same time, V generates the algebra and is the space of primitive elements. And since R generates the algebra, you have a projection from T of V to R, and this projection is homogeneous, preserves the components, and is, as a matter of fact, is a morphism of Hopf algebras. This unique R is called the Nichols algebra of V and is denoted by B of V. And actually, this B of V can be presented as the tensor algebra divided by the maximal graded Hopf ideal generated by elements on degree bigger or equal than 2. And the crucial question for the classification is to determine this ideal, or if you wish, to determine when B of V is finite dimensional. This ideal in some times is quadratic, but many times it's not quadratic. It could be even not finitely generated. So there is no actual technique to determine this ideal. Well, we found this definition, we were very happy, and then we understood quickly that there were many algebras defined in the literature that gave the same object from a different definition. The oldest one was a definition by Nichols in 75. Let me observe that in 75 there were not braided Hopf algebras, but he managed to introduce via Hopf bimodules an algebra that turns out to be equivalent to our Nichols algebra. Then Voronovich and Schauenburg looked at some algebra defined via the quantum symmetrizer. Rosso looked at the cotensor algebra. He wanted to explain the uniqueness of the quantum groups. And this is a very influential paper for us. And Lustig, also a very influential paper, looked at an ideal J, which is the radical of a suitable homogeneous bilinear form in the diagonal case. And again, this is isomorphic to the Nichols algebra. If the dimension of V is 1, then there is only one possible braided vector space, which is one possibility, which is multiplication. C should be multiplication by Q, different from 0. If the characteristic is 0, if Q is 1 or is not a root of unity, then there are no relations, so the Nichols algebra is the symmetric algebra. And if Q is a root of unity of order n, then B of V is the truncation of the symmetric algebra at the power n. And for instance, if the characteristic is bigger than 0 and Q is 1, then you get the truncation of V to the characteristic. More examples. If C is the usual transposition, I will assume characteristic 0 from now on. If C is the usual transposition, this is a solution of a braid equation, and you get the symmetric algebra. If C is minus the transposition, you get the exterior algebra. So sometimes could be infinite dimensional or finite dimensional. If you have a braided vector, super vector space, if you have a super vector space, you take the super transposition, then you get the supersymmetric algebra. And it can be shown that in characteristic 0, if C is a symmetry, then the Nichols algebra is quadratic. So it's generated by the ideal J of V is generated by the elements in degree 2. So again, I repeat what I said before. A rack is a set, a non-empty set with an operation which fixing the first element gives you a bijection, and it's self-associative. And the main example is a conjugacy class. A Tuco cycle is a map from X to X to K, K minus 0, satisfying this equation. And given a finite rack and a cocycle Q, you take K of X equal to V, so the algebra generated with the basis indexed by X, and define CQ by this formula. CQ of AX tensor AY is QXY, AX acting on Y tensor AX for any X and Y in the rack. Then given such a function Q and defining CQ in this way, you can show that Q is a cocycle if and only if CQ is a solution of the braid equation. And this can be extended to Q's going from X to G ln of K, but I don't want to discuss them. So now I will recall, I will go over the list again of the 10 Nichols algebras that survive in the solvable case. For instance, if you have X equal to the affine rack XPD, where P is a prime and D is as in this list, and the cocycle is -1, then it can be shown that the dimension of the braided vector space associated to X and the cocycle epsilon is P minus 1 to the power P minus 1 times P. So this has even order, the dimension of the Nichols algebra is even, and therefore this cannot be realized over a group of odd order. In the case of the tetrahedron rack, which it corresponds to the affine F4T, T is multiplication by W different from 0 and 1. Then there are two relevant cocycles. One of them gives dimension 72, and the other one gives dimension 5184. Now, I go to the Fomin-Kirillov algebras. The class of transpositions in S4, which I denote O42, has two relevant cocycles, the cocycle minus 1, the constant one, and the cocycle K4, which takes sometimes value 1 and sometimes value minus 1. In this example, the Nichols algebra has dimension 576. The Fomin-Kirillov algebra is FK4 is the quadratic algebra that has the quadratic relations of the Nichols algebra corresponding to O24 and this cocycle K4. And as a matter of fact, it can be proved that the Nichols algebra of these examples are quadratic. And the next example is the class of 4 cycles in S4 with the cocycle minus 1. And again, this is quadratic, and the dimension again is 24 to square. So all these three algebras have the same dimension. Again, this dimension is even, and I forgot to tell you that here, or point out that the dimension here is also even, so neither of these examples appear for a solvable group of odd order. For a group of odd order. Okay, at this point I have to say the following. We do not know why these algebras have finite dimension. We don't know. So we just know how to compute the dimension. And for the Fomin-Kirillov S5, FK5, there is only one computation by computer. So there is no proof that FK5 is finite dimensional and quadratic without the computer. That could explain us what happens. Then you may understand why FK6 is so difficult, because if you do not understand why FK5 is finite and has 8 million elements, probably FK6 or is infinite dimensional, which is what we believe now, or it has a terrible dimension. And as I said before, also we do not know why we do not know when we could stop, because you could think, if the algebra is finite, if the ideal of presentation is finitely generated, and if you know a bound for the generators, then you have to compute the generators until it's bound and use a computer algebra and provide you a dimension. But you do not know if you can stop or not, or where you have to stop. If you know that you cannot stop, the algebra will not be finitely presented, and then it will not be finite dimensional. But we do not know where to stop. Okay, I come back to Nichols algebra of diagonal type in a moment. I would like to discuss the references a little bit. So the first examples of finite dimensional Nichols algebras over non-abelian groups came in this paper by Fomin and Kirillov. and appeared in 99, but the paper is from 95, I believe. And then Milinski-Schneider had similar results, complementary results, in a paper that appeared in 2000. My third PhD student, Matthias Grania, found many of the examples I showed before in 2000, and in 2000 he published it in this paper and in this paper. And one of the examples corresponding to, so until around 2003, all the examples in the list that I showed were already known, except one that corresponds to the tetrahedron rack and the biggest dimensional algebra. And this was found in 2012 by Heckenberger, Lochmann, and Vendramin. And after many years of fighting with these examples, in a paper by Heckenberger, Meir, and Vendramin, they showed how to deal with Nichols algebra of prime dimension, of Yetter-Drinfeld modules of prime dimension, by going to characteristic P. And in our paper, we showed this for solvable groups. So it took us more than 20 years to reach this point. Okay, now to finish, I still have 5 minutes, I believe. To finish, I will discuss Nichols algebra of diagonal type. The Nichols algebra of diagonal type are those that correspond to abelian groups in characteristic 0. In positive characteristic, there are examples of abelian groups which are not of diagonal type, but I will not discuss them here. So what is a braided vector space of diagonal type? It's a braided vector space that has a basis such that for a matrix Q equal to Qij, with the same number, the same size of the dimension of the vector space, the braiding is given by CQ xi tensor xj is Qij xj tensor xi. So it's a particular case of a rack. It's a trivial rack, so to speak. Then, as I said, if V is a Yetter-Drinfeld module over a finite abelian group, then V will be of diagonal type because we are in characteristic 0. Let me give you a couple of examples. Suppose that Ni is the order of Qii, and assume that out of the diagonal is symmetric. So Qij, Qji is or multiplicatively antisymmetric. Qij, Qji is equal to 1 for all I different from j. Then the Nichols algebra, and assume that this Ni is finite. Then the Nichols algebra is generated by x1, x2, x3, x theta, and the relations are xi, xj minus qij, qji, and xi to the ni equal to 0. So this is what we call a quantum linear space. And then we replace this condition qij, qji equal to 1 by the condition qij, qji equal to qii to the power aij, where aij is a generalized Cartan matrix in the sense of Katz. Of course, for A different from J. Then we proved under some conditions that the dimension of the Nichols algebra is finite if and only if Aij is a generalized Cartan matrix of finite type. And Heckenberger, some years later, proved this, showed that these conditions that we had were not necessary and proved this in full generality. A bit later, Heckenberger proved that for any Q, assuming that Qii is not a root, is not 1, he proved that the dimension of B of V is finite if and only if Q belongs to some list. I cannot give you a lot of details. One has to say more things, but let me explain you what this list is. And before that, let me observe that one of my students, Ankiono, proved that the dimension of V is finite, so Q belongs to the list. Then the defining relations, he exhibited them explicitly. So what is the list of Heckenberger? First of all, he has Cartan type. Cartan type is when Q has this shape. When Q has this shape, we say that Q or V or B of V is of Cartan type. The second big family in the list of Heckenberger is the matrices of supertype, which I could not explain very quickly, but they correspond to contragradient finite-dimensional simple Lie superalgebras as in the classification by Victor Katz, OSP, MN, etc., etc. So in some sense, this list gives a quantization in some sense of this list of hats. But there are more in the list. Some of them correspond to super algebras, to modularly algebras or modularly superalgebras in positive characteristic, which are somehow exceptional. So what happens is that these modularly algebras and modularly superalgebras in characteristic 0, in some sense, they have a quantization in 0 characteristics. So you are going from positive characteristic to 0 characteristic. And beyond these 3 classes, there is a class that we call them UFOs. There are 11 examples that are not yet completely understood where they come from. There are some ideas recently, but not completely worked out. In other words, the finite-dimensional Nichols algebra of diagonal types come from Lie theory. Thank you.
Any questions, comments?
Yeah, my question is, what is known about the semi-simplification of the tensor category of representation of pointed Hopf algebra?
It's a very good question. If you have the Cartan type, it's more or less known, brutally speaking. And for the other ones, for supertype, my feeling is that you will not get nothing good because of the superstructure, of the superstructure. But this is an open question. I thought some time on this, I couldn't finish, but at some moment I had the feeling that you will not get anything new.
Okay. Thank you.
Any more questions, comments? If there are no more questions, this is the last talk. I suggest that we thank both the speaker and all the organizers of the conference.